All right, and we're off. So today we will be talking about graph transformer networks. So before we actually dive into the paper, I do want to give some background on GNNs, so what GNNs actually are, and specifically convolutions on graphs, and also something called metapaths, so what they are and how they are used to deal with heterogeneous graphs, so graphs with different types of nodes and edges, so how to encode that information in your model. So I will immediately jump to this wonderful review paper which I found. Here's the title, and here are the authors. So let's start with the most basic GNN here. So maybe if I zoom in a bit. Okay, so the goal of a GNN is to learn some distributed vector representation of each node, and you want so essentially you're embedding each node in some vector space, and you want to do that in a way that encodes information about where the node sits in the network and how the node relates to its neighbors and its neighbors' neighbors, and so on. So the way that this is done specifically is there is a function, there's a parametric function called the local transition function, and this is one which is shared amongst all the nodes. And essentially what it does at a high level, here's the equation, but it pulls in information from its neighbors. So its neighbors' feature vectors, the features of the edges connecting to those neighbors, and aggregates it in some way with its own feature vector and or vector representation, and applies a function to it. So normally some kind of nonlinearity, but this changes depending on the architecture, and it uses this to update the node state, the vector. And so after this is done, it is then passed into another function to produce an output. So of course, this is this is task specific. Normally what I've seen is G here is defined, is normally given by a fully connected layer followed by a softmax. So if this is for a node classification task, that's what it would be. But of course, GNNs can be used for tasks, so not just node classification, but also graph classification, link prediction, and edge classification as well. Okay, so for ease of notation, so these vector representations for each node can be stacked, and so you result in, so the result is a global transition function here and global output function. Okay, so for the original GNN, from what I've read, the state for each node is actually a fixed point of the global transition function if you assume that it's a contraction map. So under this assumption that if you were to take any 2 points in the embedded vector space and apply the function on them, the output 2 points will be closer. This is what it means at a high level. Then you can reach the fixed point, the fixed point vector representation for each node by just iterating on the function. So and this is by the Banach's fixed point theorem. So and also you can think of iterating on the function as one iteration. The first iteration, the node learns about its neighbors or receives information from its neighbors, and as the second one, it receives information about its neighbors' neighbors, and so on. And of course, once this node representation is learned, it is passed to an output, it is compared with some ground truth. So in the case of node classification, there is target information on each node, and a loss is computed, and so learning happens in the usual way. So so gradients are calculated with backpropagation and updated with gradient descent. So I think that's all I wanted to say about the original GNN. Oh, there is another point about the state embedding being a fixed point. So it doesn't, this assumption here, this is discussed in the limitations section here. You can relax the assumption of a fixed point and instead treat iterating on the function as analogous to a layer in a feed-forward network. So in this way, you can design a multi-layer GNN, because sometimes having to iterate until the node representation converges can be expensive. Okay, so I think that's all I wanted to say about GNNs. Are there any questions, any comments so far? No? Okay. Let's move on. So I wanted to talk about convolutions on graphs. So from this point in the paper, there is just an explosion of different variants of GNNs. So with graph data, there is a lot of information that you could possibly want to encode in your model. So edges can carry weight. You might want to include that. Edges can be directed, undirected. There could be different types of nodes and edges, which we will talk about here soon. But yeah, so this is a wonderful diagram of all the different types of graph neural network variants, and we will take a closer look at this one here in particular. Okay, so in terms of convolution on a graph, there are spectral approaches and non-spectral approaches. So we'll talk about a spectral approach, which relates directly to the GTN paper. But essentially, I don't want to go into too much detail here because of time, but the convolution operation is defined, is first defined by the eigenspectrum of the graph's Laplacian. So this goes into spectral graph theory, where where the interest is spectral properties of matrices which describe the graph. So you could use the Laplacian. And
sorry to interrupt. There's a question in the Q&A.
Oh, there is. Okay. While I'm sharing my screen, I can't actually see. Oh, okay. Let's do this. So the question is, what is usually the input format to a GNN? Is it the usual edge list? So do you mean the input format in terms of like practically, in terms of how you would represent the graph as a data structure? So what I know about the input is there are features on all of the nodes and or edges, and there can also be vector representations on top of those, or the features can be used as the initial vector representation. But I think the answer to the question is yes. In terms of how you would represent the graph as a data structure. Does anyone have anything to add to that? Okay, somebody raised their hand. How do I add you? Just a moment. It's because while I'm sharing my screen, I can't see the other options. Okay. I'll figure this one out. So what I'm going to do is I'm going to stop sharing and do this. Okay, so I just added, I believe it's pronounced Inike to the chat. Sorry, I don't know of any other way to add somebody, but here we are. Okay, we're back. So did anyone want to add anything to that, to the question? No? Okay, so let's carry on. All right, so where was I? So convolution on a graph. So as I said, to reach the final GCN that we're interested in, essentially what is happening is the convolution operation is defined by the eigenspectrum of the Laplacian, and then some number of approximations are made to avoid having to actually diagonalize the matrix. So we see here that this is the convolution operation. I just want to note that this applies to a scalar for each node. Of course, we are interested in a vector for each node, and it will be generalized to that in just a moment. But yeah, so this is the decomposition, and there is a parameterized filter on the eigenvalue matrix here. So the way that this is approximated to, as it says here, to remove the need to compute the eigenvectors is the filter is, do I have any more questions? So the filter is approximated by Chebyshev polynomials. And again, this removes the need to actually diagonalize the Laplacian. It's a useful approximation. So to move to GCNs, the polynomial order is restricted to 1. And some other approximations are made. Now, in terms of these approximations that are made, I'm not sure exactly why they are made, other than they allow the model to be defined and be used in practice. So I'd welcome any input here in terms of, I guess you could think of this as some kind of parameter sharing, or yeah. So some number of approximations are made, and eventually we reach this expression here. So we have the renormalization of the degree matrix and the adjacency matrix as such. X is the input signal, so there are rows for each node, and C input channels. So C doesn't necessarily have to be the dimension of the vector space we want to embed nodes in, but it can be at the start. Of course, you can, through layers of your GNN, reduce the dimension, and so here the convolved signal matrix can have vectors for each node of a lower dimension as well. Okay, so that is our talk on GCNs. I think we have something in the chat. Oh, okay, Ovid has to go. All right. Okay, are there any comments, questions up to this point? No? Okay.
I guess you could add that why is it called the convolution, even though it's not really a convolution, right? Because
would you like to speak on that? Yeah, I'd like to hear that.
Yeah, it's just because I remember when we had the first talk on GCNs, that this question was asked, and I think it's an important question because basically here we assume a fixed convolution, right? So normally you would learn the matrix, but here we assume it's fixed, and it's the graph topology, which is the well, t minus half a t minus half, right? So we would assume that's basically the convolution, which is not learned, but it's fixed for each graph. So this new paper we will talk about kind of covers that, because here we are assuming the graph is homogeneous, right?
Yeah. So thank you, Vahan. There is a point in the paper about this being a fixed convolution, and we will talk about that. So I think that's everything I wanted to say here. So there's a part here about metapaths to deal with heterogeneous graphs, but I think I would like to move to the actual paper now. Okay, so so the paper is on GTN. So the problem that the paper claims to solve is that GNNs don't work particularly well on fixed and homogeneous graphs. So sorry, not fixed and heterogeneous graphs. Heterogeneous graphs are ones where there is some information about the graph of different types of nodes and different types of edges, and you want to find a way to encode that in your model to make the most of that information. And also, and this seems to apply more to large-scale graphs, there may be edges which, so you may not be able to trust necessarily the connection between any two nodes at that level of granularity. So there may be some misspecification in your graph, but there must be still ways to learn from it. Okay, so that's the abstract. So the introduction here mainly talks about how to approach the problem of including heterogeneous information in your graph. So it first of all gives, it gives a naive approach, which is to forget about any heterogeneous information, treat your graph as homogeneous, and then just operate on that, which of course is cheating, because it doesn't allow you to exploit that information. Another way that this is dealt with is with something called metapaths. So there is a description, there is a notational description later, but at a high level, what metapaths are paths in the graph which are connected by heterogeneous edges, and that represent some connection between your different node types, which is meaningful. And so it says that, so they say that the metapaths in the past have been manually designed. So as an example, for a citation network, if the problem is author classification, you might define the author paper conference paper author metapath, where you have a graph structure or a collection of graph structures connecting these types of nodes together in this way. And you would then operate your GNN or GCN on that structure. What this paper proposes is a way to learn the metapaths. So the tasks can be the model can learn to perform on tasks with the least amount of manual input necessary in an end-to-end fashion. Okay, so there's some talk here about previous methods for the task of node classification. I think I would like to jump to the method here. Okay, so in terms of notation, you can think of your heterogeneous graph as a collection of graphs, one for each edge type. Now, I do want to make a point here about edge types and node types, and I would like to hear people's opinion on this. But it says here, in this paper, we consider the case where the number of edges is greater than 1. So there's nothing about the number of nodes being greater than 1. And in cases where the edges, the edge types are defined by the connection between different node types, I can see how this would apply for different node types. But in situations where there are actually different node types and different edge types, I'm not sure how this would apply. Does anyone have anything to say about different node types? No? Okay.
It's a good question. It's just maybe they just don't cover that case. Do they claim that they cover it?
I mean, at the start, they do. They mention node types and edge types, and it does deal with different node types in a way, because if the edge types are defined that way. So, for example, if you have a citation network with author paper conference, then the edge types are defined by author paper or paper conference, and so that you can deal with everything at once by just looking at the edge types. But in terms of the distinction, I'm not sure. Okay, so thank you, Vahan. So the heterogeneous graph can be represented by a graph structure for each edge type. So specifically, it's represented by adjacency matrices for each edge type, and this can be so your entire structure can be just represented as a tensor. So so n is the number of nodes, and you have k edge types, and of course each node has an input feature. Okay, so so here's a good here's a notational definition of metapaths. So you're interested in finding a path connected with heterogeneous edges, and the way that the metapath graph structures are defined is by taking by matrix multiplying the adjacency matrices for each edge type. So yeah, as it says here, as an example, you could take the adjacency matrix for author paper edges and paper conference edges and matrix multiply them, and then you have your adjacency matrix for your metapath for your metapath graph structure. Okay, so this is the architecture. This is the type of GNN that is learned, that is used on top of the metapath graph structures that are learned from the original graph. As you can see, it is exactly what we looked at in the, okay, I'm not on that page. We looked at in the review paper, except that in the paper, this H was an X and this was a capital theta. Yeah, so there is a point here that it relates to something that Vahan was saying earlier, is that the first half of this expression represents a fixed convolution which only depends on the graph structure, and the things that are actually learned are the part that is learned is the node-wise linear transform, and this is the weight matrix. So because the metapaths are learned and GCN is applied onto those metapaths, you can think about this this first half of the expression as no longer being fixed. It is indirectly learned by the metapaths that it has to operate on. So it makes a point here. It allows it leads to virtually various graph convolutions using multiple metapath graphs. So yeah, so that repeats the point that Vahan made, and yeah, so I don't think there's anything more to say about here. We covered the GCNs earlier. Okay, are there any questions, any comments at this point? We've got something
hello
here. Hello, yes.
Yeah, this is Ineka. So yeah, very nice paper. And I have a question on if you have heard about the transductive and the inductive learning. So in the original GCN paper, they claim that this GCN the graph coefficient network is able to do the transductive learning, not the inductive learning, because in the transductive learning, the network will receive the whole data set as a training set and then predict on that set also. So it's different it is different compared to the normal supervised learning that we do, that the test set is a blind test. So have you ever heard about it? Because what I'm thinking is that if the GTN network claims that it can learn a new graph structure, so can we implement this in the inductive learning setting instead of transductive? But I don't know if you have heard about this transductive and inductive
I mean,
learning.
I haven't learned of those in this context, so I can't really answer your question, I think. But yes, so it applies on the entire graph structure, and so this is a way to find the most emergent substructures and work on those. In terms of transductive and inductive, I guess I need to look into that more. But thank you for the question. That seems interesting.
I might have something more to add there, because thanks, Ineka. Actually, very interesting comment, because here they also mentioned that when you build the tensor of adjusting matrices, so each matrix there can represent a separate graph, right? So they mentioned that this can actually be used to learn on multiple graphs at the same time. Is it related to what you were saying?
Yeah, because in the GCN original paper, they claim that they train and predict on the same graph. So it's not the situation where, for example, we have a IMDb review data set as our training set, and then we use it to predict any other review data set. That's what they claim in the GCN. That's one of the drawbacks. So I'm just wondering if using this way, where we can learn new graph structure, can we then approach the problem as inductive, even though we're using the GCN? Yeah.
It is possible, but maybe it's a new research paper then, I would say.
Yeah. Great, thanks, Owen.
Okay, interesting. Thank you, guys. That's a new trajectory, possible research trajectory there. Okay, so yeah, so we discussed GCNs. So okay, so how are the metapaths actually learned? Okay, so at a high level, let me zoom out this page a bit. At a high level, what is happening is the architecture learns to select, to softly select two adjacency matrices from the collection, and then the new graph structure is just given by a matrix multiplication of these two adjacency matrices. So I say that it is softly selected because it isn't necessarily, 2 out of the k adjacency matrices are picked out and then matrix multiplied. The selection is actually a convex combination of adjacency matrices, and these are the, so it's by one by one convolution, and these weights are actually learned. So the way they are learned is there is a parameter over the there is a parameter vector over the different edge types, which a softmax is applied to, and these are then used as the coefficients of the convex combination. So yeah, so the diagram is pretty clear here, I think. So softly selecting two adjacency matrices and combining them to bring out an emergent graph structure. So in this way, you can allow for connections between nodes which are not connected in the original graph. And so you can essentially, the idea is to discover connections between nodes, rather relationships between nodes which are not necessarily connected directly in the graph, in the original graph. Okay, so there's a point here about the representation capability of this meta path generation part of the GTN. I'm not sure how clear I am on this. I'd like to hear what others think about this part. But essentially, what is done is so you can see here that as you matrix multiply multiple adjacency matrices, you're increasing the length of the meta path, and so at the elf layer of the GTN, you will learn length L metapath graph structures. So if this is for one layer, then you will be then this is repeated. This matrix multiplication is repeated across all of your layers, and so they do something with they do something with adding the identity matrix to the collection. To be honest, I'm not actually sure why this is done. So I'm not sure I'm convinced, but I can read what their justification, which is that so it allows for the inclusion of original edges, original connections in the graph. So you can think of it as some kind of feedback loop where you're not only operating on emergent edge connections between nodes that may not have been connected, but you actually include the original connections as well by adding the identity matrix to the collection here. Does anyone want to add to that point? No? Okay, let's move on. So, okay, so we finally reach the actual architecture of the GTN. So what was described here in this figure is a GTN layer. So so what happens is this is repeated a number of times, and that is defined by the output, the number of output channels of the 1-by-1 convolution. And so then these C adjacency matrices are then used as input to the next layer, and the same thing happens until after a certain number of layers, the adjacency matrices are then passed into a GCN and concatenated. So this is essentially what this equation this equation describes here. So as the task to benchmark this architecture is node classification, then so after the high level node representations are learned, then this is then passed into, or rather are computed. This is then passed into two dense layers followed by a softmax on the classes of interest. So are there any other things I wanted to say here? So this architecture. Yeah, so it says it can be viewed as an ensemble of GCNs on multiple meta path graphs. So ensemble by concatenating on the different channels. Okay. So in terms of experiments, the baseline, so the data sets used are 2 citation networks and the IMDb data set. There are 4 edge types for each one, so that's nice, equal baseline. Yeah, so I don't know if I have much to say about this section, because let's skip to the results, I guess. So yeah, so it repeats, it reaches state-of-the-art performance in terms of F1 score on node classification task on these data sets. It even beats the architecture that I thought this paper would be about, which is the graph attention networks, where there is actually an attention mechanism on the graph. I don't know about you know, you guys, whoever read the paper before. I assumed that this paper would be about applying some attention mechanism on a graph structure, but actually that is what GATs are. So I guess if somebody would like to present that in some at some point in the future, then you're welcome to.
Did we have the GAT paper before? Maybe last year sometime. Maybe Joao remembers.
Oh, was it presented already?
I don't know. We had a couple of GCN papers, but I don't remember if this one was there.
Okay.
Maybe not. If not, we should do it.
Yeah, we'll see. Okay, so thank you. So yeah, so this is this. So these are the results. It's on one task. There's a point here about including the identity matrix in the collection of adjacency matrices. So again, this is to, they say this is to include some of the original structure in your model, the original node connections, and again, reducing them. So not including the identity matrix causes a drop in performance. And yeah. So there's this section here about the interpretation of GTNs, which I think is quite interesting. And yeah, I'd like to hear what anyone else thinks. So the idea is you know that the metapaths learned by the network are good if once you apply a convolution on them and you learn through that. If you can achieve state-of-the-art results, then you know that the metapaths learned are good. But how do you know that they are good in and of themselves? Like, how do you interpret them, and are they meaningful? So the way that this is done at a high level is there is a score that is assigned to each to the contribution of a metapath, and the ones with the highest score are then compared with what would be predefined manual input metapaths on the data sets. So so the table here is of interest. So these are the predefined metapaths. So again, for the citation network, it would be author paper, conference paper, author, and the learned, one of the learned metapaths in the GTN is exactly that one. So in terms of how this is exactly done, so you can think of an adjacency matrix that is generated as using the output of the previous layer as well as the collection of adjacency matrices that are produced as well. So the attention score of interest is this product here, and this is what is used to determine. I think there's a better point here. So it provides the importance of the meta path in the prediction task. So yeah, I think that's all I wanted to say about this part. Does anybody have anything to add? No? Okay. So yeah, so the figure here shows the attention scores for the edge types, and yeah, so there's a point here. By assigning higher attention scores to the identity matrix, the GTN tries to stick to shorter meta paths, even in the deeper layer. So there's a point about the identity matrix allowing you to include original connections in the graph, and so essentially it means for an L layer GTN with the identity matrix, you can learn an L+1 length metapath, and so it seems like even then the model tends to stick to shorter metapaths. Okay, so I think we've reached the end of the paper. This is the, I can't actually remember what is said in the conclusion, but I guess it just summarizes what the paper is about. It would be interesting to talk about an actual attention mechanism on a graph if that hasn't done before. We can definitely do a paper on that. Okay, so I think that's all I wanted to say. I think we can open up for questions now. So if anybody in the chat or in the call would like to ask any questions, we can spend the last 10 minutes or so discussing the paper.
Yeah. So I wonder for the training for the batch size, how can we do mini batching to train this GNN? Because as far as I understand that we need to send the whole network, which is the batch size is the number of the nodes.
Yeah.
Yeah, but then what if we have millions of nodes? How can we strategize to do a mini batching for the training?
That's a good question. I'm not sure how mini batching would be done there. Yeah, because it's interesting if you think of each node as the equivalent to, you know, like an observation in a data set, and because we are learning about you know, where each node sits in the wider network, I'm not sure how mini batching would be done actually. Does anyone have an answer to that question?
Why is the problem? Because the Jalsi matrix is too large, or?
Yeah,
So
for example, if we have millions of nodes, and then how can we implement mini batching, or do we have to have the batch size as big as the number of nodes?
I don't think we have to have batch size as big, because well, first we can pre-compute the Jalsi matrix, right? It's fixed, and it's sparse, so it doesn't take much memory. And if you don't have weights, it's also binary, right?
Right. Yeah.
So I think it should be okay, but I haven't actually checked the details.